Hello everybody. Today we will discuss two topics which are important in the context of quantum computing. One of the topics is quantum interference. Before I introduce the concept of quantum interference, actually I need to tell you that there are three quantum phenomenon which are very important as far as the quantum advantage is concerned. So one of the phenomenon is quantum superposition. The second phenomenon is quantum interference, and the third phenomenon is quantum entanglement. So today I will briefly describe about the quantum interference phenomenon, which is very important as far as the quantum advantage is concerned. Now let us see what quantum interference is. Interference is the phenomenon that allows certain computational paths to amplify correct results and cancel out incorrect ones. This is the interference that we used to study in our school classes when we used to study the constructive and the destructive interferences. So exactly the same type of concept is here, that when the constructive interference takes place, the phenomenon will allow certain computational paths to amplify the correct results. Now, what is our goal? Our goal is to amplify as far as possible the likelihood of the correct results and as far as possible suppress the incorrect ones. This ability depends on quantum superposition and the phase of the quantum states. So it is the phase actually that will determine whether there is constructive interference taking place or the destructive interference will take place. Unlike classical probability, basically which adds probabilities in the case of classical systems, quantum computing adds amplitudes and squares the modulus at the time of measurements. So in quantum computing, what happens is the probability of getting a result at the time of measurement is basically proportional to the amplitude square, quantum amplitude square. Now let us consider two paths leading to the same basis state, ket x, and let the total amplitude be psi x, which is the wave function or the amplitude for the time being. Let us consider it to be an amplitude, to be the total amplitude is the wave function equal to alpha 1 plus alpha 2. Alpha 1 and alpha 2 are the amplitudes related to the two paths that we are trying to discuss, which are actually taking the result to a common eigenstate, common basis state, ket x. Now what should be our goal? If the correct answer is ket x, then then quantum interference, what should it do? It should make the possibility of the measurement result, which is ket x, as much as possible. Now constructive interference occurs when the phases align. For example, both amplitudes point in the same direction. So these are the two amplitudes, alpha 1 and alpha 2. Alpha 1, because these are all complex numbers, so we can express alpha 1 in the polar form as a e to the power iota phi, and alpha 2 is b e to the power iota phi. Now when we sum, because these two paths are going to the same ket x, and let us sum the two amplitudes and we get psi x equal to a plus b e to the power iota phi. We know that the probability is given by the modulus of the psi x square. So if we do it, a plus b e to the power iota phi square, so this is going to be 1. E to the power square of iota phi will be equal to 1, because that is basically cos square phi plus iota sine square phi, which is 1. So we are left with a plus b whole square. So therefore, what is constructive interference? When the two phases are such that they align with each other and the two amplitudes are added with each other, and as a result we get a boost in the amplitude, thereby the probability of the of the Ketex state, probability of the quantum state which is most likely the correct result. So we are maximizing the probability of getting that state. Now in the case of destructive interference, what will happen when the phases are opposite to each other? Now alpha 1 and alpha 2 are there, so the phases are out of phase with each other. The two amplitudes are out of phase with each other. So one is phi, one is phi plus pi. So therefore this alpha 2 will be equal to minus b e to the power iota phi. So when the two amplitudes are added, we get a minus b e to the power iota phi. And if it is possible that if a is equal to b, then actually the probability will go to 0. But let us say that even if it doesn't go to 0, it will be minimized as far as possible. So the probability of measuring x is eliminated. This is the case when the state which is not likelihood, which is not the correct result, so that probability we have to actually minimize as far as possible, and that we can achieve through destructive interference. So constructive interference for the measurement output which is the most likely, and destructive interference for all the other outputs which are incorrect results. So that's the basic principle on which the quantum interference works, which gives us the amplitude amplification which is for the correct result. Now another quantum phenomenon that I need to discuss is phase kickback. Because these are small topics, so I just thought that let us consider these topics in one video, and it can be, these topics can be explained within the specified time. So the quantum phenomenon is phase kickback. Now phase kickback happens. When it happens, let's see. So consider the quantum circuit. Let us consider this quantum circuit. This quantum circuit is a 2-qubit circuit. One input is ket plus, which is basically equal to ket 0 plus ket 1 divided by under root 2. And the other input is ket v. Let's say it is ket v. And we apply these two inputs to a controlled U gate, right? Controlled unitary gate. So let us not worry about what is unitary, but both these inputs will be applied to certain controlled unitary gate. We try to look at the qubit status or the quantum states at every point in the circuit. Let us see the quantum state, let us see the status of the quantum state at ket psi 1 and ket psi 2. So what is ket psi 1? It will be the tensor product of ket plus and ket v. So that's what exactly I have shown here. Ket psi 1 is equal to ket psi tensor with ket v. So, and we can express ket v as 1 over under root 2 ket 0 plus ket 1 with v, cron with v. Now what is v? This is important. Ket v is actually the eigenstate of u. Now this is a condition for the phase kickback. Ket v should be the eigenstate of this controlled unitary. Controlled unitary is a matrix. So when you try to find out the eigenvalues of controlled this matrix, then ket v should be the eigenvector corresponding to the eigenvalue of this matrix. So this is a precondition. So therefore ket v is the eigenstate of u. So when u is applied on v, when this u acts on ket v, we get e to the power iota phi ket v. So this is e to the power iota phi basically are the eigenvalues, since all eigenvalues of quantum computations can be represented by e to the power iota phi. Now as I said, ket psi 1 is the tensor of the two qubits. If we try to solve it and take ket v inside the bracket, we will get ket 0, ket v plus ket 1, ket v, right? And this is when this is ket psi 1 before you apply the controlled U gate. But let us see after we apply, let us try to find out ket psi 2, which is after we apply the controlled U gate. So ket psi 2 is the qubit status after we apply the controlled U gate. So controlled U gate applied on the first term, which is ket 0 and ket v, plus controlled U gate applied on the second term, which is ket 1 and ket v. In the first case, the control qubit is 0, so therefore control unit will not have any effect, so therefore we get ket 0 and ket v as the output. But in the second case, when we apply the controlled unitary, then what happens is control qubit is 1, which is this qubit, which is the qubit that we have obtained from ket plus after doing some mathematics. So this controlled unitary acts on ket v with control qubit as 1. So therefore this ket v, basically what will happen is controlled unit, nothing happens to first superposition as control qubit is 0. That's in this case. So in the second case we get e to the power iota phi ket v. So that's what the controlled unitary does the operation. So therefore ultimately we get 1 over under root 2 ket 0 plus e to the power iota phi and ket 1. If we take out ket v as common, so we will get with this. So what happens is that when we apply the controlled unit gate on ket v, so basically this unitary is an operator. So if you try to, let me just explain this point. If you try, so you have Cu, which is an operator, and it acts on ket 1 and ket v. Let us drop this ket 1 because this is the control qubit, and of course this tells us that control qubit is 1. Now Cu acts on ket v, right? So this is an operator acting on ket v, which is the eigenstate. That's why I was saying that this is very important, that ket v should be the eigenstate of ket u. Now if you apply the eigenvalue equation, this should be equal to the eigenvalues, which are e to the power iota phi, and the eigenstate itself. So that is why I get this value here, e to the power iota phi ket 1 ket v. So when you take ket v common, so you are left with this. This is important to understand what happens actually and what is phase kickback. Now can you see what has happened to ket v? No change. Ket v, there is no change in ket v. Ket v earlier was also there, so it stands out exactly the same way, right? So no change even though it was the target qubit. A factor of e to the power iota phi has been applied as a relative phase to the control qubit. So what happens to the control qubit? A factor of e to the power iota phi, which is a relative phase, is applied to the control qubit. So this is known as phase kickback. Control qubit gets the relative phase as a kickback. Therefore, we name this term as phase kickback. So this occurs, but this occurs only when the ket v is the eigenstate of the controlled unitary. So this occurs if ket v as an eigenstate of the U gate, and we call this phenomenon as phase kickback. So if you have a state ket v, which is an eigenvector of U, applying a controlled U gate with ket v as the target, then we get a phase kickback onto the control qubit. The eigenvalue e to the power iota phi acting on the target has been encoded as a relative phase in the control qubit's superposition. So this is important, and this is known as phase kickback, and you must know that how the phase kickback happens and on which qubit the phase kickback is having its importance, and that to the control qubit when it happens when cat v is the when this cat v is the eigenstate of the controlled unitary, this unitary matrix. So these were the two topics I just wanted to cover in this video. Thank you very much.